Hey, welcome back. In this video, we're going to start a series on applying Taylor series. Importantly, before we get started, we need to talk about some common Taylor series that we've seen previously and have derived, but you need to have in your notes in order to really functionally work with a lot of the stuff we're about to talk about. And first on our list should not be a surprise. It's 1 over 1 minus x. If you've been following along, a lot of the power series conversation was started with this one, which is derived from simply an investigation of the geometric series. Importantly, this Taylor series representation has an interval of convergence from -1 to 1. And then you've hopefully seen many of these, the e dx and sine of x we developed with this concept of Taylor series. And then the cosine came from the derivative. And then tangent here, tangent inverse, was actually a use of this first one, manipulated to get the 1 over 1 plus x squared. Then we took the integral, but I digress. Anyways, this is a solid list. If you look at any textbook or any resource, they may have more or less than these right here, but it would be expected in this course that you have at least these in your arsenal on a note card and ready to use in any application. First on our list of applications is how to evaluate a limit using these power series representations. Now, in some of these cases, you might think there might be a different process, such as L'Hopital's rule that I could use, but it's important to understand how we can use power series in tackling more complicated limits. And one of the most classical limits that you'll see in early calculus is the idea of taking sine divided by x. In this case right here, we have the sine of 2x divided by x. We're being asked to evaluate this limit, and I'm going to do this with a power series representation. First and foremost, what I'm going to do is I'm going to represent sine of 2x using the sine of x Taylor series representation. And now remember this with power series, we're allowed to compose these powers of x with these coefficients. And so I'm allowed to plug this 2x in for here and here. And the resulting will be a power series representation of sine of 2x. So I'll write that out real quick. All right, so here I have it. Again, all I've done here was copy the power series representation of sine of x. I need to make sure that the value for x I'm going to is on this interval of convergence. And we have this infinite domain for which, or infinite interval of convergence for which this series represents this function. So we're just fine. What I'm going to do then is divide both sides of this by x. And so the expression sine of 2x divided by x can be represented by this statement right here. And now what I actually want to do is take the limit as x goes to 0. So what I'm going to do on the next step, I'm going to introduce the limit to this expression right here. And then instead of writing it like this, it's always a bit easier to expand it out a little bit. Let's do 3 or 4 terms. And then we can see how maybe we can interact it with the x. And before I do that, whenever you're doing these tricks of attacking these expressions with the power series, look to represent just the complicated functions. In this case, the sine of x. I'm not thinking about how do I get x involved in the power series. It will interact with the power series itself. So then the limit as x goes to 0 of the sine of 2x over x equals the limit. And again, let's expand this series a little bit. So it seems like there's a lot going on, but let's just plug in one at a time here. So plugging in a 0 gives me a 0 here, so I get a positive lead coefficient. And then 0 here gives me a 1. So this is 2x to the 1 power. So we got a 2x over 1 factorial, which is just 1. I don't need to write that, but I'll throw that in right there. And so now if I plug in a 1, so if k equals 1, I get 1 power of the -1, which makes this negative. This is an alternating series. I plug in a 1 here, I get 2 plus 1 is 3, so this is 2x to the third. Just for the purposes of board space and what I want to write out, I'm not going to write 2x to the third. I'm actually going to apply that exponent of 3 to both those factors, so I get 8x to the third, and this is over this 3 factorial, again, because k is equal to 1. 3 factorial is 3 times 2, which is 6. And then let's just do one more of these terms at least. If k equals 2, this is going to be positive, which I already put right there. 2, this is 2 to the 5th, or this is 2 times 2 is 4, plus 1 is 5. So 2 to the 5th and x to the 5th. 2 to the 5th is 32. And x to the 5th. And then down here, this must be the factorial of 5, so it's 5 factorial. I actually know 5 factorial is 120, but you could just write 3 factorial, 1 factorial, 3 factorial, 5 factorial, but I'll throw in some of those numbers there. I know the next term is going to be negative in this alternation, and on and on. But importantly, this discussion, this is just the expansion of this series right here. We are dividing by x. And since we have these additions and subtractions, and we're dividing the whole series by x, we can use the concept of distribution to apply this division of x to each of these terms. And when I do that, so this will cancel out this x right here, this will make this an x squared, and this will make this an x to the 4th. And then all the way down, instead of having these odd exponents, we're going to have these even exponents. But interestingly, because of the limit we're calculating here, we only actually care about what's happening to those first few terms. Specifically, as I'll simplify this in the next step, you'll see that actually all that ends up mattering is that first term right there. But let me just denote this canceling of this x with all of those terms in each of those terms in a series. So what this becomes, so the limit as x goes to 0 of sine of 2x over x is represented by, or is equivalent to the limit as x goes to 0 of this series right here. So it'll just be a 2 over 1 or 2, and then minus x squared 8/3, but let's call that, or 8/6, excuse me. We'll call that 4/3. We should reduce that a little bit right there. Plus, and again, we should reduce this. These are both divisible by 8. So this is a 4 and that's a 15. I really don't need this, but hey, I'm a math teacher. Might as well keep all my fractions reduced. So we have 4x to the 4th over 15 and yada yada. The important thing here is in the beginning, as remember when we deal with limits, the tricky or interesting ones are these ones that are undefined at the point at which we're trying to find the limit. So the issue was we couldn't use direct substitution because we can't plug in 0 into this statement right here. But in this representation, importantly, how this series allowed us to cancel this factor of x in the denominator, we now can plug in 0 into each of these terms. Importantly, to this process, we're guaranteed with the structure of this infinite series right here is that we'll always have at least one power of x in the numerator, and we'll not have any situation where we have this division by 0 because these are positive increasing powers of x and they're in the numerator. Long story short, I can plug in 0 into this. Each of these terms all down this series go to 0, and the only thing that survives is this lead term of 2. So in order to evaluate a limit statement using power series, the only thing you really need to worry about is if the value of the limit is within the interval of convergence for a power series that you've chosen. Of course, when you're attacking these need to be nearly the same as these functions that we're representing here in order to use a power series. But then after that, all you're looking to do is usually you want to expand this. You could do it more in a condensed sigma form, but it's almost always easier to see it in its expanded form. Expand a few terms, see what the interaction between your series and the algebraic statements that are around it. And once you've made that analysis, see then with some canceling and tricks like that, whether you can now directly evaluate by plugging in that value to the terms of the series. Important to that, as I tried to highlight when I was doing this, you need to make sure your series is of a nature that allows the move you're trying to do. And again here, I was guaranteed, given the nature of this power series, that I would have at least one power of x that I can cancel in each of those terms.